Saxon Advanced Math, Lesson 79B. These are roots of complex numbers. Now, let's talk about roots first of all. It's one of those things where people get really confused when we say roots, and they don't like that name because it doesn't bring anything up in their head. What is a root? Well, first of all, if we rewrote this, and I see a little error here, this is supposed to have a 3 there, I apologize. If I look at that and I say, what's the cubic root of 8? Well, that's 8 to the 1/3, or 2 times 2 times 2. That is going to be one of the roots. 2 is one of the roots of 8. The other two happen to be complex, and we're going to talk about those complex roots. It's really hard for us to think about what those complex numbers would be without converting them into a polar format. And let's move forward here and we'll look at these using our previous known knowledge of multiplying complex numbers. In polar format, I remember I can multiply these and I add these. And this previous part of lesson 79 was the theorem that said, hey, that works out really nice, right? 2 CIS 12, 3. And if I took that and I said, well, that would be 8 CIS 36. This is the first third root, or the third root. This is the first version of it. And that gets confusing, but this is the basic one, right? This is the one if I said 8 CIS 36 to the 1/3, I would say, oh, 8 to the 1/3 is 2. And a third of 36 is 12, right? That's how we got to there by saying 12 plus 12 plus 12. That was, 36. And 2 times 2 times 2 is 8. And so I could go back the other way and say the cubic root of 8 CIS 36 is 2 CIS 12. But there's a couple of other roots in there. 2 CIS 132 and 2 CIS 252 also work out. Now we're going to talk about how we get there, but let's look at the pattern here first of all. If I realize that if I said this, let's just make sure that works. 2 times 2 times 2 is still 8. 132, 132, 132 is 396. Well, 396 happens to be, if I were to look at this, taking away the 360, I would end up with the 36. So in other words, I could say 360 plus that 136, or what if I did it the other way around and said 360 divided by 3, because I have a cubic root, and I say 120 plus 12 is 132, and that's where this number is actually coming from. So if I say 360, because that would be a full circle, right? Divided into 3 equal pieces means each one of these roots of the 3/3 roots of this number are going to be separated by 120 degrees, and that's always true. The 4th roots are separated by 90. Okay? And I can just take that 360 and divide it. So this number, 360 divided by 3 is 120. I could say 12 plus my 120 and get 132. And it does work. If I went back to here and I said, well, remember that sometimes we had to take away 360? What if I added 360 and I got 360 plus my 36, right? And then I said divide that number there, which is 396, divide that by 3, I get 132, 132, 132. So if I'm looking at this pattern, I realize that there are other numbers that would reduce back to being correct. 360, well, what if I went another 360? So I added 720 and got 756. That's going to give me 252, 252, 252, but when I multiply them out and I reduce it, I end up with my original, which was my 36 again. So if I look at it and say 8 CIS 36 actually has 3 roots. 1, 2, 3. Here they are. 2 CIS 12, 2 CIS 132, and 2 CIS 252. Now, how do I come up with these roots? There's an easy way to do this, and we're going to say if I just was given this problem here to begin with and said find the 3/3 roots. Okay, well, all right, I'm going to say 8 to the 1/3 power, right? 8 to the 1/3 power is 2. I'm going to take a third of 36 is 12, and that's my first root. Then I take 360, divide it into 3 equal pieces, so 120 degrees, so every 120 degrees, this root pattern will work out again. So I'm going to take that and add that to 12 and get 132. Add it again, add another 120 and get 252. And there are my 3/3 roots that reduce back to the original same original number. And so 8 CIS 36 has 3/3 roots. Now, let's look at example 79.3. And I've got examples all over the board here. I apologize. I'm trying to get as much onto this as I can. 79.3, find the fourth roots of 16 CIS 60. Now, let's take this and say we want the fourth root, and there are 4 of them. That's pretty easy. So the fourth root would be 16 to the 1/4 power. Well, that's pretty easy. That's 2. And I take 60 and I divide it by 4, right? Because that's what root I'm looking for. And 60 divided by 4 gives me 15. And so now I realize that my first fourth root, the first one I'm going to find of the fourth root, is going to be 2 CIS 15, right? Because if I took 2 CIS 15 times 2 CIS 15 times 2 CIS 15 times 2 CIS 15, I say 2 times 2 times 2 times 2, which is 16, and 15 plus 15 plus 15 plus 15, which is 60. There's my first root. That's the easiest one. Then I realized that 360 degrees divided by 4 is 90, so my second fourth root is going to be 90 more than my first one. So I just add that on there, okay? And I realize it's still going to give me the same thing. So I keep adding that same root, so that the second is going to be 105, 195, 285, and I'm just adding that on. Notice the 2 stayed the same. Now, if we check this out, we checked that one already, we know it works. How about 2 CIS 195? That's your second root, right? If I did so, or your second fourth root, if I did this, I would say 195, right, times 4, which is 780, minus 360, right, because I can keep subtracting those, or 720, that's going to give me 60. And I get 16 CIS 60 again. So it works on this one. Let's try it with the last one, right? The fourth root. So I have the first, second, third, and fourth root. If I tried on this one, the 285, I would say 285 times 4, right, which is 1140. 2 to the 4th power, 16. So 16 CIS 1140. I can take away 4 sets of my 360, or about 3 sets of my 360. So 360. 360 is 720 plus 360 again is 1080. Subtract that and I end up with 16 CIS 60. So it works again. So here are my first fourth root, my second fourth root, my third fourth root, and my fourth root by just adding 90 to each one of those. And the way I got 90 was just taking 360 divided by 4. Now, let's look at a little more fun one here. This is where we're starting to get back to our original, which said the first root of the cubic root of 8. The third cubic root, right? Or the first cubic root of 8 was 2. Let's look at if we said find the 3/3 roots of -1. Now, this is where it all kind of comes together in my mind. This is what I've been trying to get to here, because this all of a sudden makes sense. So let's take this -1 plus 0i. Where do they get the 0i? I can always make a non-complex number into complex by adding a 0i. It doesn't change the value. If I graphed that out, and I went ahead and graphed it so you can see, it would be all the way around at 180 degrees at the -1, right? Because it's up and down, the 0, none, and it's left 1. Okay, so -1 plus 0i. Well, how would I convert that? How many degrees is it from here to here? 180. And I would still say it had a radius of 1, because if it's on that line, right, the distance from here to here is still 1. So I'm going to have 1 CIS 180. Now, notice that it's not a negative. Radiuses are positive in this case, and the 180 degrees tells me where it is at. So that's why it's not a -1. So 1 CIS 180. Well, if I took the cubic root to find this, just like I did up here, right? So we're picking up right here. I take the cubic root of 1, which is 1. That's easy. I take 180 and I divide it into 3 because I'm finding the third root, and I get 60. So now I realize that my first root in the complex number set is 1 CIS 60. Because I'm doing the third roots, I take 360 divided by 3. That gives me the 120. If I add that to 60, I get 180. Add 120 again, I get 300. I can't add it again. It would give me over a 360. And that's why there's only 3 third roots. There's not 4 third roots. There's only 3 of them. So when I write this out, I end up with 1 CIS 60, 1 CIS 180, and 1 CIS 300. Let's convert that back to rectangular form and see what happens when I do so. Because these are true. These are absolutely true. I have a cosine of 60. Okay, well, that's fine, 1 over 2. And the sine of 60i, which is root 3 over 2, right? And I always get 1 plus root 3 over 2i. Let's go ahead and do that with the 180 one, right? 1 CIS 180. Well, that 180, the cosine of 180, okay, no problem. The sine of 180, 0. Negative 1 plus 0i. And then our third one is going to end up as 1/2 minus root 3 over 2i. Right? Because it's still the cosine of 300. It puts us in the fourth quadrant, and that's a 60 degrees. All students take calculus. The cosine's positive, but the sine is negative. So 1/2 minus that. Now, when I do this, I realize something that I want to point out earlier. If I just would have said, what's the cubic root, right, of -1, you would have said, oh, I know how to do this. -1 times -1 times -1 is -1. And there it is, hidden in here in a complex 0i. -1 is the common root. This is the one that we automatically we come up with. Notice here is our root that works without a complex number necessary, because it's 0i. And here are two complex roots of -1, the complex cubic roots of -1. So this is where we come all the way back to here. We could do this with 8 as well. It has two complex numbers, but we automatically think of 2, and that's where that one is going to land. That's the cubic root of that, using this same method. Now, let's go ahead and look at the last example we'll do here, and that's 79.7. You're going to like this because once you have realized how this all looked confusing, how simple this is to actually do. Find the fourth roots of 42 CIS 40. This is where you get to use that calculator you pay so much money for, right? I say 42 to the 1/4 power. That's easy, that's 2.55. Then I take 40 and divide it by 4 and get 10 and say, there's my first root, 2.55 CIS 10. But I need to find the second root, the fourth root. Well, the fourth roots are going to be separated by 360 divided by 4, which is 90. So they're going to be separated by 90 degrees. So I just say 90 plus 10 is 100, plus 90 again, 190, plus 90 again, 280. And I bring my 2.55 down. So there are my fourth roots of 42 CIS 40. And now that you see how easy that is to work with, if you're not doing any kind of conversion, you can see that this is a very simple problem to calculate using the idea that there is more than one second root. There's 2 second roots, there's 3 third roots, there's 4 fourth roots, and that's limited only by the fact that we go all the way around the circle on the complex set. But most of the time we only have one real root, and that's what we end up using in real life, the real root.